Okay, so what we will touch in this presentation. First thing, a short introduction about what X-ray BPM electronics. Then what we actually have and what we actually had also at Libera. What it's the actual implementation, so how it looks like. I can mention it looks like a Libera Spark, more or less. Then what should we envision for the future of our XBPM electronics? So where should we move, actually? And then what we thought that can be okay, like a new, let's say, a new proposition for the XBPM electronics. So as an introduction, where we are in the particle accelerator. We are in light sources, and we are at the front end of the beamlines. So we are not anymore in the tunnel, not working anymore with electron BPMs. Also, we are not working with charges here. We are just working with the light, with the X-ray light. The detectors are usually two types. Now we are, users are adding a third type. First are blades, which are this kind of steel. They are like steel metal sheets here. And the light just crosses the center of this detector, and based where it's closer to to the other point of steel, it generates a higher current. Second type of detector, it's the CVD, the diamond detectors. Same principle. We have also here 4 quadrants. Here you can see a PCB made with Rogers material. This is from CVDEC, but many users, they produce their own diamond detectors. And here the detector itself divided in the 4 portions. And the concept behind is the same like in BPM. What is different is that here we are sensing currents, and sometimes we need also a polarization. It can be high voltage, but at high voltage we talk about 100, 150 volts. What's the story behind in Libera? So everything started with the platform A in 2010. This was the first Libera photon that we produced. And you can see it's quite similar somehow to the Libera Brilliance. Then the next step was the platform C Libera Photon, which was developed in 2016. And it will be running for additional years. So now it's 8 years of working history, but we plan to use it till, I hope, till 2030. And the next generation is the one that will be based on Korea. This is what we envision as a potential candidate. It's now in internal development. But as you can see here, it will not replace this instrument. They will go in parallel. Also because they are not the same instrument. There are a few differences. If we check about hardware and software, what changes between these 3 platforms? The first one had an internal high voltage source. If I remember correctly, was about several hundred of volts. While in the other one, we don't have it. Usually the final user provides it. The ADC, it's quite different. On the first one, we had 300 kilosample per second, higher resolution, 24-bit. Now we will keep 2 megasample per second with 18 bits. The FPGA itself changes quite a lot. Virtex second, which was developed in the early 2000s. Now we have Zinc 7020, the same like Spark, Libera, BIMBOS monitor, and the next one for Korea will be the Zinc Ultrascale. Current ranges are also slightly different between the first edition and the next instruments. Here we talk about 2 nanoamperes, so also thanks to the benefit of the ADC, we're going to much lower currents. Now, we saw that this is not so much needed. Usually we operate in the microampere range. And then another crucial point is the fast orbit feedback integration. This instrument had it, platform C doesn't have it, and now the reason why we are looking for Korea is that probably we will need it for some operations. And the third one, it's and the last one, it's for the power supply. So 220 volts PoE, then probably again 220 volts. Here it's, let's say, how it looks inside in the box. You can see platform A was composed by several modules. So this is the main board. Here is the high voltage, the current meter and high voltage unit in one box. They were connected by themselves together. In platform C, we have only one board. So it's all on one PCB. While with Kriya, we will go again to this principle. So different modules, different PCBs stacked together. Why? Because probably from the logistics point of view, we can reuse quite a good part of this main board. I mean, not only the Kriya some, but also the carrier board that will be developed. Shortly, about Libera Photon, what we actually have, what the users have. It's a platform C instrument, so Ethernet with power over Ethernet, 1 gigabit Ethernet output for fast data streaming, same shape like all the Libera platform C instruments. On the back, we have the 4 inputs, which are made with triaxial connectors. This is why we have also some guarded. We use the guarded connector because we want to avoid also the leakage current. But in some setups, we also don't need it because the high voltage it's not so high. We can have just a few tenths of volts of difference. And what's interesting is that around in the world we have more than 200 of these instruments. So it's compared to the other BPMs, it's a small niche in Libera, but actually there are many instruments. Mainly in Asia, we have SSRF, PAL, and SRRC, and then IHAP, which is now working on the installation for the new ring. What's inside? Really briefly, we have 4 channels, 4 transimpedance amplifiers, the 4 ADCs, and then the data that are samples from the ADCs, they go to the zinc for the DSP part. Also here, DSP, really briefly, same concept like more or less Spark, ERXR, or the other ones. Just we go in the time domain processing, no DDC, no strange things. We get the ADCs, we have on first averaging to get the TBT data. We can correct for dark current and use the matrix for the BPM. And then we have 2 infinite impulse response filters to get the fast data around kilohertz of that rate and slow data around a few hertz of that rate. And for sure also the post-mortem buffer. So why are we considering Kriya? So in the new light sources, probably customers will need some fast orbit feedback integration as well. Not only the current platform that's running. And we start thinking about how to do it. One first option was using like the Libera Digit 500 as a new photon BPM electronics. But we should somehow redesign the board. So getting from 500 megasample per second ADC to this 2 megasample per second. It will require some effort to do that. Second one was to integrate the gigabit Ethernet streaming from each instrument with an aggregator. So working on a new, it's FPGA-based board to aggregate all this data, group them, and then send them to the fast orbit feedback control. Also, this is quite complicated. Or the next solution that our colleague thought about, it was using the Kriya. With the difference of previous like Xilinx and like Zinc, it's not anymore a system on chip, it's a system on module. This means we don't have only the FPGA and the ARM processor, but we have a bunch of other things. We have the memory, power supply, don't need a lot of stuff. And as performance, if we compare it, this is the Zinc 7020, so our current Libera Photon. We have, for example, 85K logical cells. The Digit 500, which runs with Zinc 7035, had 275, and Korea has 256. So we can say that Korea and the Zing 7035 are somehow comparable in performance terms. Next requirements that I'm also still collecting, still discussing, they are about the, let's say, the other features of the BPM. One is the high voltage. Sometimes some people requested about extending the high voltage up to 500 volts. This is feasible, but will not be done for several reasons. First, it's because of recertification of the entire board. We have to demonstrate that this will not kill a potential user during operation. And the second one, which we will implement, actually, it's the possibility to monitor the high voltage that is currently applied to the detector. About the current measurement functionalities, we will probably add the auto range, which is already done on the Libera current meter, which is somehow the cousin of this of the Libera photon. The calibration, so to read out the data not in ADCs but in current values like picoamps. And then on this the hardware group it's working, it's to extend the range up to 20 milliampere. This is quite tricky to do because in a transimpedance amplifier you need to keep the stability of the amplifier itself, and it's not easy sometimes. And last, if anybody ever worked with Libera photon, it's to avoid using this reverse polarity SMA because people don't like it. You have to purchase it actually to connect to the instrument with a safety high voltage, but safety high voltage actually has some other issues because we don't have this L type of connector to be placed on the PCBs, so we will stay on the reverse polarity SMA connector for the next version. So now how it will look. This is the proposition, the rendering, how the new photon based on Korea will be proposed. So we will keep, let's say, the same, more or less, shape, like not the actual photon, which is the smaller one, but we will go to something like the cavity BPM, the Libera Digit 500. So it will be 19-inch rackable 1U. We will integrate 8 channels instead of 4, so it will be more capable. About how it looks inside, now take it for the photon, but it can be really anything else developed on at iTech based on the Korea platform. We'll have 220 volt power supply, the switching power supply, the fans. So we will go from the passive cooling to active cooling. And what you see here are the 2 add-on boards where actually we have the transimpedance amplifier and the inputs for the currents. Whatever goes then here to these 2 connectors, it's what goes in digital form to the FPGA, and it's later on processed. So to go more in detail, we'll have, if we remove the 2 boards here, we'll have the Korea module, the SOM, then the carrier board, which it can be common for all the new products. Then the timing triggering board, so where we'll have the trigger input, trigger outputs, interlocks, whatever it's needed, machine clock, so on. And in the front panel, what also makes this this solution like good for the new photon. So the SFP outputs, which can be then later on integrated with the fast orbit feedback. And as you look at it, it looks, the front end looks somehow similar to something what we have on the Brilliance. And to conclude, we can say, okay, till now we have quite a lot of experience with XBPM electronics. It's 14 years. A good install base, it's 200 instruments all around. We are still collecting feedback from light sources. Till now we saw that there is a difference between smaller machines like, I don't know, Max 4, Solaris, and bigger machines like Alba, Soleil. And we are still collecting these requirements. So if you have any idea, I mean, it can be a comment, it can be, even if you criticize it, it's good for us now, because we get one feedback, actually. And yeah, so now it's your turn. If you feel now, or maybe even later on during the wine tasting, because wine gives, you know, some. So, thanks.
Thank you, Danilo.
Welcome.
We've managed to.
Okay.
Is there any question regarding the presentation?
Yeah.
Question.
I'll keep my contentions to the wine tasting. I'll ask the question now. So, first of all, I've probably not followed correctly. Is a high voltage supply included or not?
Okay. No, it will not be included in the next
It's
version.
still being fed in from the outside. And
Correct.
like you said, it's then certified for up to 500 volts, which can be fed in.
It will be up to 150. We'll keep it.
Okay.
Yeah.
Certification reasons.
Yeah.
Okay. Okay. And I understand, because I was at first a bit puzzled by why you say there is not compatible with FA output or no fast output feedback is supported. The reason is really that the bit rate is not compatible with other products. Is that the point you
It's a little bit
about?
It's the capability of the FPGA inside. So with the Zinc 7020, we cannot drive, expose this FA data and group them through the SFP ports. So this is the reason why we are switching to something more capable.
You cannot collect and assemble Libera grouping packets. Is that what you mean?
On that, we can do it, but actually with something external. So we.
Okay. It requires a different framework.